Cool. So let's go ahead and start. Thank you. Thank you for coming back after lunch. Hopefully, I won't put you all to sleep after as you digest. I had a few people ask if I could go over the last part on function approximation again. So I think I went through it a little bit quickly. So we'll go through it at a little bit slower pace. Um, and yeah, hopefully, this last part of the presentation on multi-agent reinforcement learning was meant to basically give you an idea of kind of current research, specifically in my group, on some of these topics, just to give you an idea of actual work that's actually happening. And so this is a little bit more advanced material, but hopefully you find it interesting and you'll see a lot of the themes that we've already discussed kind of show up again and again. So I'll go through this, quickly. This was the motivation. We're really trying to come up with scalable algorithms, right, to deal with this case where we have really large state spaces. And so our motivation was that dealing with these really large state spaces requires function approximation. But how well motivated is function approximation in games, right? And so we were basically asking if this intuition that we have from deep learning kind of ports over to multi-agent reinforcement learning, right? This intuition that if I have more data, more compute, and I use more complex models, then I could always increase performance. And so, we came up with this very toy situation in which to analyze this problem, right? In which we had a set of model classes, or you could think of them as policy classes, of decreasing expressivity. So theta 1 here was the most expressive policy class, all the way to theta n being the least expressive policy class. So theta 1 you could think of as being the largest possible neural network, right? And then theta n is maybe like a linear model, right? And the way things kind of typically work is that people first fix their model class, they choose a certain model class, and then they'll actually use it for learning. And so they'll train an initial model, and they'll deploy that model into an environment, and maybe they retrain, and at the end of it you end up in a Nash equilibrium. And so the question that we had, right, is really, should the learner always choose the most expressive model class if they want to increase their utility at a Nash equilibrium, right? And that was kind of the crux of this section. And I gave you kind of three scenarios where we could maybe answer this. The first is just in normal optimization scenarios, right? So normal reinforcement learning satisfies this property, where the environment you could think of as all the other players, right? In this case, the environment is static, so that means that there are no other players. So we're just in a single agent reinforcement learning setting. In that case, if you could optimize perfectly, if you could always solve this minimization problem, right, you're always better off optimizing over the most expressive model class, because it will always give you, weakly better performance than anything else. What was surprising is that the same kind of conclusion held true for adversarial or zero-sum environments. So when your environment was adversarial to you, the same takeaway was true, where you should optimize, if you could optimize perfectly, you should optimize over the most expressive model class possible, because it will give you a better equilibrium outcome than any kind of less expressive model class. And then what I said is that, that conclusion is not true in general, right? In kind of even well-behaved general sum games, like strongly monotone games, this wasn't true. And it wasn't true in particular in games in which Nash equilibria were not Pareto optimal, right? And basically the idea here is that if a Nash isn't Pareto optimal, you could always construct basically a restriction of your action space that yields where the Nash equilibrium in that new game with this new action space has a higher utility for you. Right? So that immediately implies, and so the proof is a little bit involved, but this implies that even with infinite data and infinite compute, less expressive model classes could actually give you better equilibrium outcomes in general sum games, right? Which is maybe that little bit counterintuitive. And I basically said, this shouldn't be too surprising if you have more of a game theory background. Bray's paradox is a well-known paradox in game theory. There's some examples in linear quadratic games, um, um, and even in comparative in game theory more generally. And so basically, I then was trying to construct an example. The details of this example are mostly in the paper, but I'll try and give you a little bit better of an explanation of what's happening right now. So we're in a two-player zero-sum game. We have two players and states, and both players just have two actions. Player two basically controls their state transitions. Whenever player two plays b is equal to 1, the state transitions to the right? And then whenever they play 0, you kind of stay in that state. And player one, even though they have no control over their states, we're going to construct the game so that their payoff is always larger in larger states. So the more the game ends up to the right, the happier player one is. Great. So then we kind of construct this nested class of policies where the least expressive policy class you could think of as just being the uniform policy. The most expressive class is just the entire simplex. Obviously the policy class is actually in R2, but this is just the visualization for visualization purposes. And the way we do this is just by basically constraining, the policy of action one and being between, p bar and 1 minus p bar, right? For p bar in 0.5 to 1, or 0 to 0.5, sorry. So this is our construction. We then construct the payoffs of the game so that player one has a dominant strategy of a equal to 0 in all states, right? And so what this means is that their Nash equilibrium strategy in every state is going to be to put as much weight as possible on action A is equal to 0, right? Because it's a dominant strategy. And then what we do is we construct the payoffs for agent 2 so that they will only trigger a transition to the next state when basically the policy of player one is below a certain threshold, right? And so basically what we do is we basically construct an instance where the more expressive the policy class for player one, the more the Nash ends up closer to this state 0, right? And so at Nash, we're basically seeing this kind of inverse relationship where the larger reward equilibrium happens at the least expressive policy classes, right? So if I could choose the class of policies to choose over, I would basically choose the class that only contains the uniform policy, right? But it's hard to know that a priori. But this is just an example of a construction where choosing the most expressive policy class hurts you. Yeah, I mean, it's a good question. So this isn't really an equilibrium selection problem because the way we've constructed it, given the policy class that you've chosen, the equilibrium is unique. So there's no equilibrium selection to choose. But you're right that it's an equilibrium selection in a kind of meta game, right? So it's not really equilibrium selection, but it's you could think of it as you have to reason about your policy in like this kind of leader follower or Stackelberg way, or your policy class in a kind of Stackelberg way. Great. So that kind of, the takeaway is just that choosing a good function approximation or a good class of function approximators in general sum games is actually non-trivial. And it can actually hurt your equilibrium performance to choose a very expressive policy class. But luckily, what we saw is that in zero-sum Markov games or in adversarial Markov games, a more expressive policy class is always help, right? And that's kind of a really nice property. And so for that reason, the next part of the talk is going to focus on using function approximation in zero-sum games and some of our recent work on that. Yep. Yeah, exactly. Just the class of policies that are available to you. Think of policies parametrized by neural networks. Yeah. Cool. So yeah, we're now going to look at function approximation in zero-sum games. Again, we're back to to this picture where we'd like to design learning algorithms for zero-sum Markov games. In particular, we're going to focus on infinite horizon zero-sum Markov games. And we'd like to design algorithms that are kind of convergent, independent, no regret. And particularly, we'd like them to use function approximation and be scalable. And basically, a lot of algorithms, even from classical economics, do satisfy some of these properties, right? So in particular, we're going to focus on today a class of algorithms known as smooth fictitious play. This is an independent, last iterate convergent algorithm in zero-sum games. That's also no regret. It was introduced by Fudenberg and Krebs in 1993 as a generalization of fictitious play. It's actually been extremely well analyzed, both in the econ literature as like a trembling hand version of fictitious play, and also using stochastic approximations by Hofbauer and Ben-Haim and Hirsch. And so what I'm going to do today is basically show you some of our work on developing a payoff-based version of smooth fictitious play. So payoff-based means we're only going to use observations of our reward. We're not actually going to use observations of our opponent's policy at all. But the version of the algorithm that we come up with is going to be rational, which means it can take advantage of stationary opponents. It's independent in that it requires no knowledge of our opponent's policy. And it'll converge in the last iterate sense in two-player zero-sum games. And what we'll show is that it retains convergence guarantees when you're using linear function approximation. And so the key idea is actually going to be based on a 2-time-scale analysis of a smooth version of smooth fictitious play. Great. So we're going to go back to our nice picture, just to give you a sense of the prior work on zero-sum Markov games. It started very, very early on by the analysis of fictitious play and best response dynamics. Early 2000s, there's a lot of work on kind of individual Q learning in kind of an asymptotic sense. And much more recently, there've been a lot of work on other learning dynamics, as we've seen in the last the last section. But all of the work in this space, in some sense, has always been missing at least one of the following. It's either not had convergence in Markov games. These were for normal form games. It wasn't payoff based, so it required maybe full observation of my opponent's policy, right? Which is maybe a strong assumption. Either these algorithms could not use function approximation, or they also did not have last iterate convergence guarantees. And today what we're going to do is come up with an algorithm that has all four of these properties. Great, so let's introduce smooth fictitious play. So the idea is very similar to fictitious play. You're going to basically, instead of best responding, you're going to approximately best respond to your opponent's empirical history of play, right? So basically at round T, you're going to compute your strategy. And instead of just solving for the argmax, you're regularized. You're penalizing from deviating too far from maybe uniform policies, right? So just think of this as a regularization. This is basically allowing you to approximately best respond to your current belief over your opponent's policy. Then you're going to play according to your current strategy. Sorry, this should be pi. Sorry. You're going to play according to this argmax. You're going to observe your opponent's action, and then you're going to update your belief, right? So this is just keeping track of your opponent's empirical history of play, right? So this is, again, just fictitious play, but instead of doing an argmax, you're just introducing a regularizer with this parameter tau here, right? Which stops you from perfectly optimizing. It penalizes you away from the corners of the simplex. Great. Yeah, so a few things about this algorithm. It assumes that you know your payoffs, right? Because you have to be able to solve this argmax. You're regularizing with entropy most of the time. And then you're keeping track of the empirical history of play of your opponent. So you have to be observing their actions, right? So this is not a payoff-based algorithm. And so it requires full observation of your opponent's actions. And so suppose that you don't know A, you don't know your payoffs, and you cannot observe A. You cannot observe your opponent's actions. How should a player learn an estimate of A pi 2 using only their own payoffs? Right, that's kind of the key idea. And kind of in keeping with the theme of this talk, the idea is we're going to do stochastic approximations on this quantity. And so this is our doubly smooth best response dynamics. This is our algorithm. The idea is very simple. You're going to play according to your current policy. You're going to sample according to your current policy and observe your reward. Then you're going to update your belief. Your belief is going to be captured by a Q function, right? Which is basically going to follow these dynamics, right? This is just stochastic approximation on this loss here. Then, given your belief, you're going to compute your smooth best response, and you're going to update your strategy on a very slow time scale, right? So the main idea is if Q is converging to your estimate on a fast time scale, this algorithm is mimicking your smooth fictitious play on a slow time scale, right? And I should mention that this is not a new idea. Using multiple timescales to stabilize Q-learning was actually proposed all the way in 2003. But what we show is that you actually don't need to use two timescales. You could actually use a single timescale and just have beta and alpha here differ by a constant, and we could actually even make that constant explicit. Great. So this is a nice algorithm because if you look at it, it's independent. This player does not have to know anything about their opponent's utility to actually implement it. More importantly, the player doesn't have to observe anything about their opponent. The only thing they have to know about their opponent is actually nothing, right? In some sense, all you have to do is observe your own reward to implement this algorithm, right? And so that's really nice because this is an algorithm where I could just deploy it and only use my own reward information, and I don't even have to know that there's an opponent in the environment to actually implement, right? But unfortunately, this so far only works in matrix games, and obviously there's no function approximation, right? Great. Any questions about the algorithm? Nope. Yep. Is what? Oh, this term? Just think of it as it's actually the entropy of the policy. Yeah, exactly. So you're just biasing this towards the uniform. It's just to basically smooth out this optimization problem, right? If tau is 0, then this is just an argmax, right? But if tau is non-zero, it basically regularizes your problem and smooths it out. Basically, it gives you curvature, and it gives you kind of smoothness of this best response, right? Because if you think about it, let's go back here. Suppose tau is 0, right? Then this is just a linear program in pi, right? And the solutions to linear programs, as I change the linear optimizate the weights that I'm optimizing over, could shift kind of drastically, right? Because it could hop from one corner of the simplex to another, right? This can't do that anymore because this is basically regularizing it. So it smooths this function out. Yeah, exactly. So that's exactly what we end up doing is we're going to decay this to 0. But if we decay it to 0 at the right rate, you preserve smoothness the entire time that you could exploit. Cool. That's a good question. Thank you. And this is a very kind of common trick. We actually have already seen it when people were looking at kind of the convergence of regularized policy gradients. The idea is it gives you curvature, it gives you smoothness, and it lets you prove fast convergence. Yeah. Any other questions? Great. So we could, actually start to analyze this algorithm. We could, define the regularized Nash gap as maybe a distance from the Nash equilibrium of this regularized function, of this regularized optimization problem. And what we could show is that our doubly smooth best response dynamics with alpha is just 1 over t, and beta t is equal to just some constant times that. And for some tau greater than 0, we get a convergence rate of 1 over capital T, right? So that's actually quite fast. And this is a finite time last iterate convergence result. We're actually proving that the iterates themselves are converging. And importantly, we're only using bandit feedback, right? We're only using the reward, and we're not using any observations of our opponent's policy to get this result, right? Importantly, we're not getting last iterate convergence to Nash yet because we're only converging to Nash in the space of policies of this regularized function. And so if we wanted to get convergence to the true Nash, we get a much slower rate. But nevertheless, this is actually the fastest known rate for last iterate convergence with bandit feedback in these games, which I think is interesting. So great. So we have an algorithm that has basically convergence in matrix games, but we haven't yet looked at how it does in Markov games. So now let's go to Markov games. Remember, we're in a zero-sum Markov game, so we're kind of in the regime of minimax Q-learning. And so we could come up with this algorithm, which is just an exact generalization of the algorithm we just saw to handle now the Markov game structure. So the idea is that we're going to use our smooth best response dynamics, our algorithm that we just saw, to solve the matrix game in each state on a fast time scale. And then on a slow time scale, we're going to do value iteration, right? So it's exactly the same ideas that we've already seen. The difference is that we're going to solve the matrix game using only bandit feedback or only reward feedback and not any observation of the opponent's policy. So this is how the algorithm goes. At every round t, you're going to play according to your current policy. You're going to observe your reward at time t, and the environment's going to move to a new state. Then you're going to update your belief or your Q function about your marginalized future payoffs, right? Given the reward that you saw. Then you're going to compute the smooth best response given your belief. You're going to update your strategy on a slow time scale. And then every k steps, you're going to update your value estimator, right? And you're going to do basically min-max value iteration on a very slow time scale, right? Importantly, this V here you could think of as basically capturing your belief over your future payoffs, right? And you're just updating that on a very slow time scale, right? So this is, again, kind of the algorithmic structure that we've seen a lot of, right? On a fast time scale, we're basically doing our smooth best response algorithm to solve a matrix game. And then on a slow time scale, we're updating the matrix of that matrix game, right? And using min-max value iteration. Great. Once again, this algorithm is independent and it's payoff based. I'm not using any information about my opponent's actual preferences, and I'm not using any observations of my opponent's actions. The only information I'm using is my own reward and the observation of my state, right? So we have an algorithm that's independent and actually payoff based. And now, again, we could look at the Nash gap, right? And this is basically capturing our distance from the Nash equilibrium in this zero-sum game. And we can actually show that if there exists a pair of policies pi1 and pi2 such that the induced Markov chain is irreducible and ergodic, this basically allows us to have sufficient exploration of the MDP or of the Markov game. Then this algorithm that I just showed you converges at a rate of 1 over t to the 1/8, right? And this is important because it's a last iterate convergence guarantee. So the iterates themselves, your policies themselves, are converging to Nash. And what's interesting is you don't pay anything for going from matrix to Markov games, right? And this is really just because value iteration converges at a geometric rate. So it's not the rate limiting factor here. Great. So we basically come up with a payoff-based or a bandit feedback algorithm that's independent and has finite time iterate convergence to Nash in zero-sum Markov games. To give you an idea of the proof, we basically, as I said, solve matrix games on a fast time scale. These slow time scale is actually pretty non-trivial because we have basically inhomogeneous or time-varying Markovian noise coming in. And actually, we lose zero-sum structure because players might have different rewards, and so they might have different beliefs over their future payoffs. And so this is actually a pretty non-trivial problem, but we kind of come up with like a particular Lyapunov analysis to actually prove convergence of this algorithm. Great. So now we have a convergent algorithm. But so far, we haven't introduced function approximation yet. And that's what I'll do in the next little bit. So when we think about algorithms for using function approximation, even in single agent reinforcement learning, maybe the most famous example is this algorithm known as deep Q-learning. Deep Q learning is basically the algorithm that allowed us to really start, um, beating all of those Atari games that Gaurav was talking about this morning, right? And so the key the key insight that we're going to use is that a timescale separated version of deep Q learning or deep Q networks can be viewed as smooth fictitious play under a basis transform, right? And so basically, the analysis that we've just done for smooth fictitious play, we could actually apply it to deep Q learning with linear function approximation. Great. So this is our new algorithm. The only difference from what we just saw is that instead of doing Q learning, we're doing basically least squares on the Bellman error. This is equivalent to what I just showed you in tabular settings, but this allows us to use basically function approximation for Q. The weights here are basically how we're parametrizing the Q function. But otherwise, the algorithm is essentially exactly the same. At each round T, we're going to play an action according to our current policy. We're going to observe our rewards, and then we're going to move to a new state. Then we're going to update our belief over our future payoffs, just using stochastic gradient descent on this least squares loss here. And then we're going to update our strategy on a slow time scale, our policy, and then every k steps we're going to basically do value iteration. Yeah, that's a good point. So we're assuming the weights might have some constraints to them. Yeah, and so you're just projecting. It's a Euclidean projection onto like the set of weights. This is actually very common in deep learning. It's sometimes called like clipping a Q function or something like this. It's normally you just have you just want the infinity norm constraints on the weights. You don't want your weights to go up. Yeah, exactly. You don't want it to go, it's just called, it's just clipping basically. And this object here is sometimes called the target network in deep learning. Okay. Great. So note that we're updating so theta here are the parameters of the Q function that we're using to parameterize our belief here. And we're assuming that beta here is much slower than alpha, right? So we're updating our weights on a fast time scale, and we're updating the weights of theta on a slow time scale. If beta was 1, we would recover single agent DQN. So now just to show you why this is equivalent to the smooth best response dynamics, suppose we're in a stateless regime. So we're just in a single state, MDP, and all of the fast time scales have converged. So gamma is equal to 0, and our weights are the argument of this object. Right? Then our DQN updates look like this, and our smooth best response dynamics look like this, right? So hopefully you could actually see that this is already pretty similar, right? But what I could do is I could just do a change of basis, right? So I could define U to be R inverse of Q, right? And then under this change of basis, DQN is exactly the smooth best response dynamics, right? And you could basically see that these two dynamics are exactly the same. So we could view DQN as doing our smooth best response dynamics on the slow time scales. Yep. Yeah, exactly. Yeah. But assuming that your estimates of the Q functions have all converged, right, on the fast time scales, on the slow time scales, this is what the two, right? And just under a change of basis, we could actually show that they're basically exactly the same thing. Great. And so now we could again consider the Nash gap of the problem, right? And again, under the same assumption that there's like an induced ergodic Markov chain, if both agents use this DQN algorithm with linear function approximation, then we could actually show the algorithm, has last iterate convergence guarantees again. So we have this property here, which is basically, coming from the geometric convergence of min-max value iteration. We have one term which comes from the convergence of the inner loop. We have one term that comes from the error due to using softmax policies. And then lastly, we have some irreducible function approximation error, because we're trying to use, we're using linear function approximation for a class of problems where it might not be optimal. tau is the weight here. Yeah. And that introduces some error as well, because you're not exactly doing an argmax. Great. But tau shows up here and here, so you can kind of like optimize it. So yeah, in the paper we actually optimize over tau to minimize this bound, but the rate is really bad. Great, but nevertheless, the takeaway is that we've basically constructed an independent payoff-based algorithm that provably incorporates function approximation, while still having some last iterate guarantees of convergence, right? And to the best of my knowledge, this was the first algorithm that had all of those properties. Great.
By the way, a very stupid question. So here we talk about deep Q learning with linear function approximation. So is there some tension between the deep and the linear?
Yeah. The reason why linear is important is that this least squares problem is going to be like convex, right? And if it's deep, then you would still do this. You would still do gradient descent on like the least squares, but this is not going to be convex, and so you're not going to have convergence guarantees there.
So like, is there any hope of using these non-convex optimization toolbox here?
I mean, you could maybe like the issue in some sense is just you're not going to be able to show that this is true. You're never going to show that that's going to be true.
Yeah, because here you have a closed form.
Yeah,
so you can just use the formula.
Yeah, exactly. So you're not really ever going to be able to show that the slow time scale is actually tracking the right thing with general function approximation, unless this objective is somehow convex in whatever you choose. In practice, most of the time that doesn't actually break much, it seems, right? But theoretically, that is kind of the rate limiting step. Yeah, that's a good question. Cool. Great. So yeah, just to recap, we basically showed that small tweaks to the pretty classic at this point DQN algorithm, basically just taking DQN and making it a 2-time scale algorithm, allows it to have strong convergence guarantees in zero-sum games when it's used by all the players or by both of the players under linear function approximation, right? Yep. Yeah, I mean, empirically, I think deep networks will probably outperform linear. But it's hard to prove things in theory, yeah. But we have some students actually coding it up and testing it out at the moment. That's a good question. You have a question? No? Okay. Great. So in the last part of the talk, I'm going to focus on some work in my group, kind of trying to move beyond correlated equilibria, coarse correlated equilibria, and Nash. And the motivation was basically that we wanted these 3 properties, right? We want algorithms that are convergent, that are independent, and individually rationalizable. And in some sense, this seems like too much to ask for general sum games, right? We've seen all of these computational hardness results for Nash, for stationary CCE, all the complex dynamics that you might get, the cursive multi-agency, the strong conditions for Nash Q learning to even work. And so we started to think about, are there better targets or are there better equilibrium concepts for us to think about in a lot of these games? And this was joint work with 2 postdocs who were with me at Caltech. Laishi has now moved to Hopkins last week, and Kishan is going to Tencent. But what we're going to do is we're going to define a computationally tractable class of equilibria for all normal form and finite horizon stochastic games. And it's going to be computationally tractable, independent of the underlying game structure. And what I'll show you is that it actually recreates human play very well in experimental data. And when I say computationally tractable, I mean that it can be computed by no regret learning on a related convex game. And the key idea is that we actually bring in ideas from behavioral economics into these problems. And we're going to assume that agents are risk averse to the randomness introduced into the game by their opponents, and as well as the environment. And we're going to assume that agents are what's known as boundedly rational, which means that agents have a systematic failure to perfectly optimize. So they optimize over the space of what are known as Quanto responses. These are both, pretty well-established features of how people make decisions. People are very well known to be risk averse in decision making, or risks, have risk preferences when they make decisions. And bounded rationality is also a very common, characterization of how people make decisions. People tend to not be optimal, right? They tend to, introduce noise into their decisions. They tend to, they tend to not perfectly optimize, basically. Yeah, so these will give rise to a new equilibrium concept, and we'll show it has really nice properties. Yeah. So yeah, we're gonna start in just finite action normal form games, then we'll go to finite horizon Markov games. So we're gonna have n players. We're gonna have finite action spaces for each of the n players. And again, we're gonna be in the setting where each player seeks to maximize their expected payoff, right, over mixed strategy. So the same situation that we've already been looking at. And we've already seen the notion of a Nash equilibrium here, that it's intractable to compute, and that it's led to many more equilibrium concepts since then. There's actually been even some other recent work by Costas trying to move beyond these equilibrium concepts to more computationally tractable concepts as well. But as we've seen, yeah, CCE and CE also have problems. But one of the other kind of downsides to Nash is that it tends to be actually not predictive of how people play in games. People don't tend to actually play games or play Nash in games. And there's kind of a long history of work in behavioral economics. Sultan won a Nobel Prize for this. Basically, because of this, people in behavioral economics have come up with more predictive equilibrium concepts based on ideas that people fail to perfectly optimize, right? So these equilibrium concepts, as we'll see, are maybe more expressive of how people make decisions, but oftentimes they don't really give you anything. They don't give you computational tractability in general some games. And so what we'll do is we'll make a kind of an alternative construction that actually has really nice properties. Great. What's interesting, so we focus on these two features of human decision making. Risk aversion and bounded rationality. There are others that you could have focused on. But what I really liked is there was some work by some behavioral econ people from Caltech, actually, who actually worked on this in kind of the early 2000s. They were running behavioral economics experiments. They had people come in and play a bunch of games. What they showed is that quantum response or bounded rationality alone wasn't actually enough to recreate the game playing that they saw from people in a bunch of matching pennies games. And that actually, they needed both quantum response equilibria or bounded rationality and risk aversion, right? To actually recreate human decision making. And so I thought that was kind of interesting. And the fact that people are risk averse is really a classic finding in behavioral economics. I'll define it in like 2 slides. But just think of it as being boundedly rational. Great. So to introduce risk aversion into games, we're going to make use of a general class of convex risk metrics. So you could think of convex risk metrics as just a generalization of the expectation, right? And it satisfies monotonicity. If I have a random variable that strictly dominates the other random variable, so maybe the payoff is always, almost surely better than in one world than the other, then the risk associated with it is lower, right? The difference and the difference is because we like to minimize risk as opposed to maximize utility, right? We're also going to ask for these convex risk metrics to be translation invariant and also to be convex, right? And many kind of classic convex risk metrics that you might be interested in, like entropic risks, value at risks, conditional value at risk, shortfall risk, or phi divergent space risk measures fall into this class of risk metrics. Sorry? Oh, that's true. It's not convex. Yeah, sorry. That's a good typo. Yeah, and so to introduce risk aversion into these games, we're going to start with this construction. Players originally are going to be assumed to maximize their payoff. What they're going to do is they're going to evaluate the risk associated with each of their pure strategies, right? If I fix my pure strategy, then all of the randomness is coming from my opponents, right? And maybe the environment. And so I'm just going to look at the risk associated with playing that pure strategy. And I'm going to define it by rho of pi minus I of the reward, given AI here. This is the risk level associated with with playing pure strategy AI for agent I. And then basically I'm going to minimize my expected risk, right, over my own policy. This might make sense because maybe you should be indifferent between actions that induce the same risk level, right? Great. And again, this reduces to really well-studied risk-averse control and risk-averse reinforcement learning paradigms in single-agent settings. But what's interesting is you could actually, just by Jensen, come up with a more conservative version of this action-dependent risk, which is the aggregate risk, which is just to take this expectation into the risk metric, right? And this is a more conservative, we call it the aggregate risk. Interestingly, there's some work in economics that say that this is actually not a bad model for how people make decisions, also, which I think is kind of interesting. And for the purpose of this talk, we're going to focus on this because the math is a little bit cleaner, but the results are kind of similar for both of these constructions. Great. So given this definition, we could actually define now a risk-averse Nash equilibrium, right? And this is going to be the natural solution concept for individually rational agents who are risk-averse. And it will say that we're at a risk-averse Nash equilibrium if no player has any incentive to unilaterally deviate to minimize their risk, right? So this is just the inverse of the normal definition because now we're trying to minimize risk as opposed to maximize utility. But it's all we're saying is we're at a Nash equilibrium on this objective here. Any questions about that? Great. So, maybe the first question you could ask is, do these equilibria always exist? And are they computationally tractable, right? So basically, what we can show is that these equilibria will always exist. And the reason for this is because if we use a convex risk metric, then this is a convex game still over a compact convex strategy set. And so a Nash equilibrium will have to exist on the simplex. What's kind of interesting here is we actually saw we actually found some work after we finished our paper by Amos Fiat and Christos Papadimitriou from 2010, which also kind of looked at risk aversion in games. But they made this kind of important assumption that you are also risk averse to your own randomness, right? And if you're risk averse to your own randomness, you actually don't even have existence. You can actually come up with a situation where a risk averse Nash equilibrium might not exist. So this construction here where you're risk averse really only to the randomness coming from your opponents is pretty crucial. Great. Any questions about that? Yeah. Yeah, a different risk averse Nash equilibrium. Yeah. Yeah, and it will always exist. Yeah. Yeah, that's a good question. It just depends on maybe the problem that you care about. And maybe it'll depend on computational factors, things like this, right? But these are design choices at this point. Yeah, but that's a good question.
So when we were taking not the risk, but the expected payoff earlier, then we also had our own randomness, right? But now we have removed that.
So here you have your own randomness, but it's not coming in the risk metric, right?
Oh, okay, got it.
Yeah. So if you look here, like your own randomness is it's an expectation. You're not risk averse to your own randomness.
So what does it mean to have your own randomness here, but not be risk averse? Like, what does that mean?
This just means that you're risk neutral with respect to your own randomness. And so the reason why I think this makes sense is because in this formulation, you're basically just mixing among your pure strategies. And the only reason why you would put weight on two different strategies at Nash is if their risk level is the same, right? So I think that makes sense intuitively. Yeah. Being risk averse to your own randomness is a little bit strange. It says it's basically trying to bias you towards maybe lower variance policies, which might make sense in certain scenarios, but it wouldn't satisfy this property here that you would just be indifferent between risk levels. Great. But unfortunately, we actually can't show that risk aversion is enough to ensure computational tractability. And even those works in economics say that you actually need bounded rationality to actually be predictive of human play. And so that brings in this idea of a quantum response equilibrium. And so to have computational tractability, we assume that we optimize over the space of quantum response functions. So a quantum response function is just a continuous function that just puts more weight on a better outcome, right? So maybe so the kind of canonical example of a quantum response function is a softmax, right? A softmax function satisfies this property, right, with a negative beta. And so basically, you could think of a quantum response function as just being, we're optimizing over the space of softmax policies. Yeah, exactly. Sorry, no, think of x as a scalar. Or yeah, x and y are scalars. Sorry, x and y are entries in a vector. And sigma is operating on the entire vector, and sigma of entry y is greater than sigma of entry. Sorry, it's a little bit confusing. But just think of a softmax, right? If x is greater than y, then the softmax of that vector will put more weight on, sigma x instead of sigma y. So basically, we could go from this original problem of optimizing our risk-averse objective over the simplex to optimizing our risk objective over the space of quantum best responses. You could think of this as just, instead of being best responses, as being better responses. It's kind of the same type of idea. And maybe just to make it even clearer, we could actually fully capture a quantum response or a space of quantum responses using any convex regularizer here, right? So any set of quantum response functions can actually just be captured with a different strictly convex regularizer over the simplex, right? And so epsilon now is basically capturing the agent's degree of bounded rationality. Yeah. So basically, if you just think of a quantum response function, it basically just has to satisfy this kind of like monotonicity condition, but the real crux of it is that it's continuous. So for example, the best response function, right, isn't continuous, right? Because it'll hop between corners of the simplex, right? But because you're regularizing with a strictly convex regularizer here, right, it's going to vary smoothly as I vary the optimization problem. Oh, the reason why it's bounded rationality? Just think of this as like a quantum response function. It should just be like a restriction of the simplex that basically should have smooth boundaries. Right? Yeah, yeah. Exactly. So think of this as you're optimizing, but you can't perfectly optimize, right? You can't get into those corners of the simplex. Yeah. Yep. Basically, every sigma is related to a specific epsilon and a specific mu, right? So just think of a softmax policy, right? A softmax policy with parameter beta in the softmax is basically the 1 over beta here, and this mu is replaced by the entropy. Yeah. Or the negative entropy. Great. And so this gives rise to a new equilibrium concept, what we call a risk-averse quantum response equilibrium. This is now the natural solution concept for risk-averse and individually boundedly rational agents. And it's going to be an RQE if no player has any incentive to unilaterally deviate in the space of quantum responses, right? And so given this definition of an RQE, what I'll now show you is that there's a class of RQE that's computationally tractable in all games. And I'll focus today on 2-player games, and the paper has kind of a generalization to n player. And the key reason why we can show this is by a dual representation of risk, which is that we could write any convex risk metric in a variational form, where instead of minimizing this objective, we could minimize this max objective here, right? Where the risk objective, where related to this risk metric is some kind of penalty function with some 1 over tau being the degree of risk aversion of the agent, right? So basically, any convex risk metric can be fully defined by a penalty function d that's convex in the first argument. So for example, when d is the KL divergence, you recover the entropic risk, right? And tau here captures the agent's degree of risk aversion, right? So if tau is 0, you're putting a huge amount of weight on this penalty here. And so you're forcing this adversary to basically play exactly pi minus I. And so you recover a risk neutral game. As tau goes to infinity, this term goes to 0. And so you recover basically a zero-sum game, right? Which is your security strategy, which makes sense. As you get extremely risk averse, you should just start to play your min-max or your security strategy. It's the safest strategy that you could play in game theory. Sorry? How do you compute this inner max? You'll see in a second. Yeah. Sometimes there's closed forms, right? If this is the KL, then there's a closed form for this expression. Yeah. Any other questions? Great. And so the interpretation for this is that basically what we do is for every player, pi I, we introduce an adversary for them. That player, even in a general sum game, is fully adversarial, but is penalized from deviations from your opponent's strategy.
Representation is if and only. It goes both ways. Right?
Yeah, exactly. And this is like classic work in mathematical finance, yeah. Great. And so, yeah, the interpretation is we're going to introduce an adversary into the game. Even in a general sum game, this adversary is going to be completely adversarial to this player pi I, but it's penalized from deviating from pi minus I, right? But if you look at this construction, we've all of a sudden decomposed this problem where the coupling between pi and pi is zero sum, right? And then pi I and pi minus I are completely decoupled, right? And that's kind of an important property here. Great. And so what we could show is basically if the bounded rationality and risk aversion parameters of player 1 satisfy and player 2 satisfy this kind of recursion here, then the resulting risk-averse quantum response equilibrium can be computed using no regret learning on a related 4-player game that I'll show you in a second. But the kind of remarkable thing about this result that got us really excited is that this result doesn't depend at all on the structure of the underlying game. And it only depends on players' relative degrees of risk aversion and bounded rationality. And it allows you to use any no regret learning algorithm like policy gradients or multiplicative weights to actually compute this solution. So just to give you a visualization of what this theorem is saying, right? It basically says that anything in this blue regime is actually computationally tractable, right? Yep. As epsilon goes to infinity, you're more boundedly rational. As epsilon goes to 0, you're more rational. Yeah. And then as tau goes to infinity, you're risk averse, right? And so let's just parse this a little bit. So this whole class here is basically computationally tractable. So it kind of makes sense that there's a gap here because we know a Nash equilibrium is computationally hard, right? And we know that approximating a Nash equilibrium is hard, right? So we should expect there to be a gap between what's computationally tractable and Nash, right? So it kind of makes sense that this area here is not in this space. As tau goes to infinity, for any epsilon that's greater than 0, it becomes computationally tractable. This also makes sense because that just means that the problem decouples into a zero-sum game for one of the players. And zero-sum games we know are computationally tractable for any epsilon greater than 0. So this result kind of nicely interpolates between what's known for zero-sum games and what's known for general sum games, right? And just by choosing these parameters, we could basically find a point that in between. Great. And so let me just give you an idea of the proof sketch here. And it also kind of gives you the 4-player game that we're going to look at. So this is our objective, right? We're optimizing, both players are optimizing over the space of quantum responses and these risk metrics, right? We could immediately use that dual representation of risk to write it like this, right? A min-max given P1 and min-max given P2. We could basically lift this game to a 4-player game, right? Now, this 4-player game, if you look at it, it has a very kind of important property. Wherein I introduced this just to make things work out cleanly. This is fine because it doesn't change the equilibrium. Does anyone notice anything about this game? Yep. So basically what I can do is just assume instead of solving this max problem, I could just treat this player P1 as just a player in a different game. Yeah. The min of the max, sorry, the max is just the min of the negative, right? So that's what's happening here, right? Yeah. Oh, yeah, that's a good point. So what we're going to show you is that what we show is that the equilibria of this game have to be the same as the equilibria of this game. Yeah, or like the Nash of this game have to be the same as the RQE of this game. Yeah. So kind of the nice thing about this game is if you look at it, it's actually a zero-sum game, right? It's a 4-player zero-sum game. These two cancel, these two cancel, these cancel, these cancel, and then all of these cancel. Yeah, the Nash of this game will be the Nash of this, which is the RQE. Sorry? Yeah, there's a kind of a very nice if and only that you could. Great. And then what you could do is just using convexity and concavity of the opponent's strategies, then you could actually show that CCE of this game coincide with Nash of this game for all parameters in this range. So you could actually show that this game is what's known as a socially concave game. And that as long as the parameters satisfy this property, then independent of R1 and R2, basically the CCE of this game coincide with the Nash of this game, and the Nash of this game coincide with the RQE of this game. Yeah, basically it's a zero-sum. It's a 4-player zero-sum game. Yeah, I mean, this is a 4-player zero-sum, so that's not always true, as we discussed earlier. But the kind of important thing is that these are pairwise, right? And that was the point that we discussed earlier. Great. So yeah, so basically what we've done is we've come up with a class of equilibria that's independent of the reward structure and that we could actually compute across all games. And importantly, this is only true because of a combination of risk aversion and bounded rationality. We had to use both of those properties together. As I said, similar results hold for n-player games. And using the same argument that we saw kind of before, via dynamic programming, you could actually show that you could compute a finite horizon RQE in the same way, just via dynamic programming. So it also extends to dynamic games as well. The question you might ask is, does this capture meaningful solutions, right? Is this a reasonable class of solutions, or is it too restrictive? And so to answer that question, we went back to some of these behavioral econ papers that actually reported their findings. And for each of these, so a lot of these papers actually reported the game that they made the people play, as well as their aggregate strategies that they played. And so what we went back and did is basically recreated that human data using RQE, right? And so this is basically what we found, is that we could basically recreate the observed pattern of play by people by this class of computationally tractable RQE to within kind of 3 decimal places. So each of these is one of the games from one of these 2 papers. And then we could basically recreate the aggregate data of people using this notion of RQE. So in some sense, it's expressive enough to actually capture interesting phenomena that we might care about. It at least captures human play in these very limited classes of games. Sorry? So these are like, they're combinations. So I think in this paper, these were all like matching pennies games, like just variations on weighted matching pennies games. The reason for that is because they're very simple games where you could actually force the Nash to be on purely mixed strategies. And then this paper had other games that weren't necessarily, they were just kind of simple matrix games that they had people come in and play over and over again. Great. So basically, the takeaway is that in some sense this is like an expressive class of strategies, or we think it's an expressive class of equilibria, and we're excited about it. Now, just to kind of keep going, we went to finite horizon risk averse Markov games, so the same kind of setting that we've been looking at, and we started to look at how easy is it to learn these RQE. And so if we assume access to a generative model, right? So we assume that we have a bunch of estimates of Ri and P, then we could actually show that we could approximate a non-stationary Markov RQE in polynomial in S, H, and this quantity here. So the algorithm that we have suffers from that curse of multi-agency that we discussed. And I think it's still an open question about whether we could actually overcome this. It's not entirely clear to us whether this is unavoidable or not for this class. The reason for this is because the size of the action space for each of these adversaries is actually almost the size of the joint action space. So we have to be a little bit careful. We don't know if this is unavoidable. But rather than kind of dwell too much on that, I actually just want to show you some actual some experimental results on this. So what I'll show you on the left and on the right are two very simple grid world environments. We're going to have two agents, a red agent and a blue agent. The red agent is going to try and get to the red square. The blue agent is going to try to get to the blue square. The transitions are stochastic. So if players can move in any of the four directions, so north, south, east, west. And if they decide to move in a certain direction, there's some probability with which they will go in a random direction. So there's some randomness to the environment. And the closer the two agents get to each other, the more randomness there is in the environment, right? And we're going to look at the case where the red is the more risk-averse agent. The blue is the more risk-averse agent here. And then we're going to make blue less risk-averse here. So this is what happens. This is at equilibrium. What we see is that the blue agent basically waits in this corner. It actually just hides in this corner, right? The blue agent is so risk averse that actually trying to make it to their goal before the horizon ends is so risky that they just decide to hide in this corner, which is a pretty safe state. And red is less risk averse, and they actually make it to their goal, right? When we make blue less risk averse, something kind of interesting happens. Blue now is the one who goes to their goal. And at equilibrium, they force red to wait in this corner, right? And then once the path is clear, red will go to the goal, right? And so again, the nice thing about this equilibrium notion is it kind of gives you very kind of believable and interesting behaviors, even though it's quite simple. If they're equal, that's a good question. I think they actually just both hide in the corner. Great. So that kind of wraps up this part. So the takeaway is that we came up with a new equilibrium notion that was rooted in more behavioral econ ideas, that was more amenable to learning than Nash, and has more desirable properties than coarse correlated equilibria, meaning that it can better recreate human play. We actually have some current work that shows that in infinite horizon Markov games, you could actually show that under similar conditions, a little bit stronger conditions, you actually get a contraction mapping, which should allow us to actually come up with algorithms for computing a stationary version of these equilibria. And so we're working on that at the moment. But that kind of wraps up the content that I really wanted to show you. So basically to wrap up the last couple of days, I hope I've convinced you that multi-agent reinforcement learning is actually an interesting but pretty non-trivial extension of normal reinforcement learning, because the kind of introduction of ideas from game theory really just makes learning extremely hard. And so you have to be very careful when you think about how you design algorithms for these problems. So what we showed over the last few days, just to give you a recap of what we showed, right? We really saw that strategic interactions break our intuition about how learning algorithms might work. We saw that reinforcement learning might be structured optimization. Multi-agent reinforcement learning was maybe a structured form of equilibrium computation, but equilibrium computation is just fundamentally hard, right? However, we saw that notions like non-stationary CCE might be feasible to learn, and we saw some algorithms for how to do that. We saw that in reinforcement learning, the environment was stationary, but in multi-agent reinforcement learning, the coupling between agents introduces non-stationarities into learning. And so this makes proving convergence of algorithms pretty hard, but we've seen kind of over and over again that this idea of timescale separation being a very useful trick algorithmically and even analytically for showing convergence of our algorithms. And then we showed that, in reinforcement learning, the role of function approximation is clear, right? If you could optimize, you should always be more expressive. But that in multi-agent reinforcement learning, choosing a function class was also pretty non-trivial, right? And that larger, more expressive function classes could yield kind of worse solutions. And I hope to convince you that there's still a lot of open questions, and that there's kind of it's kind of a fun area to work in because we really have to think carefully about how we design our algorithms for these problems. So even though multi-agent reinforcement learning is less well understood, we could build on ideas from game theory, behavioral economics, reinforcement learning to design new algorithms, right? And so this is just a list of, I think, kind of exciting new directions in multi-agent reinforcement learning. There's a lot of work on trying to understand the convergence of algorithms, fast convergence, convergence of no-regret learning, using stochastic approximation ideas, and so on. There's, I think, a pretty new line of work on coming up with new equilibrium concepts, including the work that I just talked about. There's a very recent paper that also came up with not a risk-averse equilibrium, but a robust equilibrium concept. Daskalakis and them have been looking at kind of smooth analysis, so trying to move away from worst-case characterizations of Nash and looking at smooth version of Nash. There's other formulations of convex games that might be more amenable to learning, like convex Markov games or Stackelberg Markov games. And then there's a lot of people who are working on, function approximation for zero-sum Markov games, interested from kind of this idea of game playing. And then, there's many, many other directions, right? Here's a small list of them: robustness, solving sim to real gaps using incomplete information, and so on. So it's a really kind of rich and kind of exciting research area. And it's a research area that's really at the intersection of three fields, which is why I think it's so interesting. So hopefully I gave you a sense of the challenges and some intuition for how you might design algorithms and how you might approach the problem of multi-agent RL. And here are just a bunch of resources that might be interesting for you. So the first is a set of talks from a Simons Institute bootcamp on learning in games from 3 or 4 years ago. So there's a really great overview of multi-agent reinforcement learning, kind of in the vein that I just gave, by Chi Jin from Princeton. And then Costas also has an overview of equilibrium computation. So it's all at that link. There's this one survey here, which I think is actually quite good for multi-agent reinforcement learning by Kaixing Zhang and his co-authors. And then here's a book. It doesn't really deal with multi-agent reinforcement learning, but it does deal with learning in games and online learning, which I think could also be useful. But with that, happy to take questions, and thanks for listening for the last 2 days. Thanks. Happy to take questions.
So I have a question. So this last thing that you described, do we think that this is also maybe how these AI agents like these players of StarCraft, etc., might play? Like maybe they also have things like risk aversion, and while they may not be boundedly rational, but maybe they can be approximated somewhere by bounded rational agents.
Yeah, I mean, I think it could be a good model for it. I think we have to investigate it a little bit more. I'm very interested in kind of going deeper onto this because I think we've only scratched the surface. So yeah, I think it could be a good model for any kind of imitation learning like task, right? That we might care about, including all these game playing problems.
And the question is that how much is the price of this? So in the sense of the amount of utility that an agent gets. So if there's like some epsilon amount of bounded rationality, how much does the agent actually pay?
Yeah, that's a good question. Again, it's not entirely clear, right? Because of that function approximation argument that I made. Sometimes bounded rationality could help, sometimes it could hurt. And it just really depends on the structure of the game. So in zero-sum games, for example, it hurts you, right? Yeah, in general, it's not entirely clear. There are some So, sorry, let me see. So this paper here basically came up with they called it a strategically robust equilibrium. You could think of it as this RQE that I came up that I proposed is a regularized version. The risk is coming in through regularization. This one might be the risk is coming in through some kind of constraint. But here they showed you that sometimes these robust equilibria are better. So for example, robust equilibria might solve, I think, like Bray's paradox. It doesn't happen in the space of robust equilibria. So some of these robust solutions might have better properties. I think it's still pretty, people have to investigate it a little bit more. Great. Awesome. Thank you so much. And do check out these resources. I think if you're interested in this area, the talks at this bootcamp are very, very good and concise and maybe more, make more sense than the one I give. Thanks.
So let's thank Eric again for a wonderful bootcamp.